Today we'll look at mapping and localization. So in terms of learning outcomes for today, I would like you to have a knowledge of navigation and the requirements of navigation. We'll be looking at maps and how to build maps. We'll be looking at how a robot helps to localize itself within a map, so we need to consider errors associated with data, and then given that data, how to extract features from that data, and then given that, how do we use them features to then localize the robot. So we'll be looking at them different aspects, and then we'll finish today's tutorials with looking at planning paths through the environment and optimizing these paths into actual paths the robot can follow. Navigation consists of 3 tasks. So we want to map the environment. So there's 2 options for this. We can either have a pre-stored map. So this is generally where will be our starting point for our robot. We'll give it a map of where it needs to move through. But we also have continuous mapping. So this is essentially if you don't know the environment and you have to map it out. But also if you have a map, that map might change over time. So for example, objects may move, or you might have dynamic objects, for example, another robot in the scene. So you continuously have to map, even if you do have a map to start with. Once you have that map, you can then go about determining what route you need to get through this environment. So ideally, you'll be wanting to go from location A to location B and avoid obstacles while doing that. So route determination will help you accomplish what is the best path to take. The final part is to then move. So you're moving along this path, and as you move, you'll continually have to update your position so you know where you are along the path. So this is localization whilst avoiding collisions. Now the chances are when you move, you'll have to move off the path, and therefore you'll have to go back and maybe change the path slightly to account for this difference. And also as the map changes, so as you're taking more scans and objects might appear in the environment, you then have to replan your route and then move. So this is an iterative process where you're continually mapping. You might be updating your route and then you're moving through this while always trying to work out exactly where you are on this path. So we'll take the first aspect of this, map making. So the easiest way for a robot to move around is to pre-program it. So this is applicable in sort of factories, industry, where the robot has got a specific job to do. So you can either pre-program it to move certain paths. So it might be along painted strips or guide wires in the floor or beacons, for example, in the factory. So it's a good way for a robot to move around, very repeatable, a robust way, but it's inflexible as well. So although it's suitable for an environment where you're going to have a lot of repetition in the robot's job, if you want something a bit more sort of typical of an unknown environment or unpredictable environment, then you need something more flexible. So ideally what you want is some kind of artificial intelligence incorporated into your control of the robot. The first aspect of this is storing a map of the environment, and the way we store this map is very important. The map consists of pieces of data, so it could be a location or it could be a feature, for example. Each of these data points has to be homogeneous. When I say homogeneous, I mean it has to be very clearly defined as it either is an object or it's an empty space. So we need each data point ideally to clearly signify if that data point represents an object or space in that environment. So we'll come to some examples where that is not necessarily the case, as you'll see. So in terms of how we build this map, or an efficient way of building this map, what we'd like to do is minimize non-homogeneous space. So it's very difficult to get a scenario where we know if exactly every point in space is either an object or free space. So we kind of have to have a balance between clearly defining a space as either totally empty or filled with something. So what we want to do is kind of minimize any ambiguity in when we define an area or volume to have that as non-homogeneous. So that is potentially part space, part object. So minimize non-homogeneous space is our first objective. Second objective, map complex shapes. So if you take a typical room, a room is usually rectangular, so that's a fairly easy shape to model and store. But you can imagine a lot more complicated shapes. For example, a table, it's got 4 legs, a top, it's quite a complex 3D shape. So how do we map these shapes and store them efficiently in our map? Third point is maps large homogeneous areas. So for example, if we have an empty room, that is one large space. If we have a room filled with tables and chairs, that is part objects and part empty spaces. So in terms of saving our data, if we had one large empty room, it'd be good to save that as one data point rather than having it recorded as lots of individual spaces within that one room. So ideally we'd like to map large homogeneous spaces efficiently. Good for local and global maps. So if you imagine a robot moving around a building, the building has got lots of rooms. So a local map might be a map of that one room. And then a global map is a map of the building in which each of these local maps or rooms is stored. So if a robot's moving around, it doesn't need to access the whole map of the building. It just needs to access a map of the room it's currently located in. But if it then moves to another room, it has to then locate the map for that room. So you can use that for planning navigation. So you want your overall map storage to be suitable for storing both local and global maps, and the local maps are easy to retrieve from the global map. Maps change over time, so for example you might want to move a table into a room or move 2 chairs out of a room. So we have to allow for map construction and modification. And then the final point of having a map is to be able to plan a path through it. So the map has to be suitable for both path planning, and also using it to help the robot locate itself within that map. So that's what we'd like in terms of a map. In terms of satisfying all these criteria, that is going to be very difficult to achieve all of these different things. But the way we decide to store a map, some of them points will be more, we'll be able to satisfy some of these points better in some map constructions to other map constructions. So we'll have a look at different ways of building a map and see which areas or which criteria it's more suited to. So as I said, maps can either be predefined, so we put a map in the computer, or the robot does mapping, either as a map from, if it's a totally unknown environment, it'll build a map from the beginning, from a completely blank sheet. Or if it has a map already built there, it might use its sensor data to update or modify that map. When you are building a map, the robot has to move around. So bear that in mind. So you can't just build a map of somewhere just from one point. In order to complete a map or build a map, the robot has to move around within that map. As you're building the map, we've got 3 options of how we store the data. We can build them, or we can save data points as objects. So we can make a list of all objects within a space. We can make a list of all space within a space. Now you don't have to record all space. What you record is the space that is available for the robot to move in. So for example, it's equivalent to a corridor where the robot can move along. Or potentially we can build a map that identifies both objects and space. So if we look at object-oriented maps, so this is where we store the data as an object. The object is going to be a certain shape. So again, because we're talking about planar robots, we'll just think about shapes in 2D. There's our shape. So the best way of describing that object is the corners of the object. So we would say a series of XY coordinates corresponding to the corners of this object. If you know where the objects are, then the robot knows where to move because it just avoids the objects and keeps to the space outside of this, which is free space. The other option is rather than record the objects, we record free space. Now, as I said, you're not actually recording all free space, you're just essentially recording paths that the robot can move along. So if we take this line here, this is essentially a space corridor. The robot is free to move along there because it knows there's no objects. If it wants to get from here to here, it cannot go directly because it doesn't know if there's objects in this area or not. So what it has to do is move along these corridors. So it can move along one of the space corridors to a junction and then select another space corridor to walk along to get to where it wants to go. Now we can construct these space corridors from our object maps. We can do that by what's called construction of a Voronoi diagram. So as a Voronoi diagram, what that does is given a certain space or certain area, this one, this has got objects in here. It's got an object, object, object. What a Voronoi diagram does is divide that area into smaller areas, and each area corresponds to a location on that map that is closest to that object. So for example, all the space in here is closest to that object. All the space in this area is closest to this object compared to any other one. So if we perform this, you can see for each object we have in the environment, so for each of these objects, then we've defined an area that is closest to that object than any other object. And that is what's known as our Voronoi diagram. In order to construct this, so these are the instructions on how to construct it. What you do is you take your objects and then construct paths through this. So we'll work through that as an example. So what we do is we take our centers of our objects, and then for objects that are next to each other or are going to share a Voronoi face, what we do is we connect these objects as such. If I can connect them with straight lines. So we connect that up. We then bisect these lines. So we find the midpoint of all these lines. And we draw a line perpendicular through. So it has to be perpendicular to this line here. Should be one there. So I haven't drawn this very accurately, but you imagine the principle. And then what we get is, if you see where these intersecting lines are, so we just highlight these a bit more. Then using this method, what we're doing is constructing our Voronoi diagram, and these lines are the perimeter of the Voronoi faces. or the perimeter of the cells, is then defining our space corridors between objects. So given an object, and we want to avoid the robot bouncing into these objects, by constructing this diagram, then this gives us our space corridors that the robot can move along. We've got a junction here, you can decide to go up this way, for example, and that way it can avoid objects. So that was the procedure. And if we take our object map and construct our Voronoi diagram, this is a completed version. And then if the robot starts here and it wants to get to here, say, it can move along these lines, avoiding objects, getting to where it wants to go. There are limitations. In that example, every object was roughly the same size. So you can imagine if objects are different size. So in this case, we've got a small object and a large object. So if we use the algorithm directly, you would actually collide into an object. In this example, we've got a very concave shape to the object. So again, we'll crash into the object. A better algorithm to use would be to use the perimeter of the objects rather than the actual center. So the center was just a simplified version. What you'd want to use is the perimeter, and then that will give you your Voronoi face there in that example, and like that in that example. So in practice, the calculation's a bit more complicated, but you've seen the basic principle of how it works. Another way of making a map is what's called exact cell decomposition. And what you have is, this is your room. So there's your room defined here. Here's your objects. And then for the node or the corner of each object, this is a point in which you can divide the room up. So we'll draw a line down there. There's a node there, if I can draw it on. So the line goes down there, a one to this node, etc. So you're dividing your space up into smaller spaces. And then, for example, if we calculate the center of area of each of these spaces, if I can draw a circle on that. You can see if we want to move around, then potentially go to the center of area to get around our space. So this is very good in terms of preserving all the environmental information. So you've got an accurate record. So you've got no non-homogeneous space defined. So everything's either defined as space or object. And it's very efficient at mapping large spaces. So for example, we've got a large space here, which is just stored as one data point. A large space here, which is just stored at one data point. So in that respect, it's very good. However, if there's a lot of objects, so if you have a dense population of objects, you can get a lot of these different smaller cells being produced. So it can get quite complex, this scenario. The composite space map is probably the simplest way of mapping. It's conceptually the simplest. What you do is you divide your room into, or your environment into squares of a certain size. So you just break it up into squares. So this is typically, I'd recommend about the size of a robot. So if the robot is, say, 20 centimeters in diameter, then it's probably a good idea to have the size of this to be about 20 centimeters for the square. So depending on the size of the robot, you want these grid squares to be approximately the same size as the robot. Divide this area up, put your objects in this map, and then you've either got a grid square that is empty and is space, or you've got a grid square that's got an object in. The slight downside to this is what's the non-homogeneous space. So for example, in this grid square, it's part object. If you see this grid square here, this grid square is part object and part space. In cases like that, you have to define it as an object. So it's non-homogeneous space, but you don't have any option but to define it as being an object space. So what you want to do is the blue is the actual objects. The red is what you've actually mapped as being the object size. When things are aligned with the grid, it's not too bad a scenario, but you can see in this case here, when something is misaligned with the grid, then the object actually appears a lot bigger than what it actually is. So it's less good at producing an accurate map of the environment. However, it is sort of conceptually simple to do and very easy to implement. I said the grid size should be typically about the size of the robot. It's up to you what grid size you want. If you go for a large grid size, then you have a low resolution map. It doesn't take up much memory and it's very quick to process that map in order to plan a path through it. So it's very quick analysis. However, it leads to very poor descriptions. So you can imagine here, if we had a big square represented here, if there's a bit of an object on that, then you would class all this as an object. So you're increasing the amount of non-homogeneous space, so it's a very poor descriptor. On the other hand, you could go for a very small grid size. So it's a good descriptor, high resolution, good descriptor. And therefore you're minimizing the non-homogeneous space in your map. However, the downside of that, it takes a lot of memory and a lot of processing in order to do anything with that map. So it's really personal choice what size you want in terms of the map. But as I said, the recommended starting point would be roughly the size of your robot to be the size of your grid square. The quad tree, I'll just mention briefly, is a variation on the composite space map. So rather than going for fixed grid square sizes, you have variable grid square sizes and you just increase the resolution when there's an object nearby. So you can see in the top half of this figure, it works to a certain extent. You've reduced the number of grid squares. However, in reality, when objects are not aligned with the grid, you still need the same resolution. So there's pros and cons to the method. So that finishes our introduction on mapping. So what we want to move on to next is looking at data from sensors and how we use that to localize ourselves within a map. The first thing we have to consider though is the errors associated with that data. So we'll discuss that in the next video.